Good morning, students. Welcome to this video session. I remain Samuel Chukwuemeka, aka Sam Done for Peace. So let's get on my website. In this video session, we shall discuss your Module 6 exam study guide. Your Module 6 exam covers the contents from Module 5 homework and Module 6 homework. So please, it is highly recommended that you review the Module 5 homework study guide and the Module 6 homework study guide prior to viewing this video. Question 1. Sam tosses a coin 100 times and gets 84 heads and 16 tails. Based on this result, determine the probability that the next toss results in a tail. So in this case, we look at the sample space, which is 100 times 100, and the cardinality of getting heads is 84. The cardinality of the heads is 84. And the cardinality of the tails is 16. So the probability of getting a tail is 16 out of 100. And you simplify the fraction to get 4 out of 25. Question 2. 40.9% of 3-year-olds in the city of Boring, Oregon, there's a city, Boring, Oregon, are enrolled in a daycare. What is the probability that a randomly selected 3-year-old from that city is enrolled in a daycare? So, this one is straightforward. Like we talked about in the introduction to probability. Probability can either be expressed as a fraction or decimal or percent. In this case, the probability is expressed as percent, but you just convert it to decimal by dividing by 100. So that gives you 0.409. Question 3. Assume the events E and F are mutually exclusive. Mutually exclusive events are two events that cannot occur at the same time or that cannot occur simultaneously. So determine the probability of E or F. So we have the addition law. This is the addition law of probability. Probability of events E or F is equal to probability of event E plus the probability of event F minus the probability of events E and F. But for mutually exclusive events, which means the events cannot occur at the same time, the probability of events E and F will give us 0. So you just add these two probabilities. 0.30 for the probability of event E and 0.47 for the probability of event F. And that gives you 0.77. or 77%, or 77 out of 100. You can express probability in any of those three ways. Question 4. E and F are two events. Probability of E and F is 0.1. Probability of event E is 0.2. Find the probability of event F given event E. Okay, find the probability of F given E. So this is like a conditional probability. And that is the formula right here. That the probability of F given E. Probability of F given E will give us the probability of E and F divided by the probability of E. So some students get confused on this formula. you know, especially at the denominator, whether they will write F or E here. Okay, this is the way to know it. I mean, this is probability of F given E. So you are already given E, and you want to find F. Okay, probability of event F given event E. So the event E is the one given, not event F. So you have to write the probability of event E because it's the one given. That is what you write as the denominator. So that will kind of make you to remember, you know, or you say the last one here. And when you do that, you get 0.5. Question 5. Assume events E and F are independent. Determine the probability of E and F. And you're given that the probability of event E is 0.4 and the probability of F is 0.8. So this is the multiplication law for independent events. So you just multiply those two probabilities, 0.4 times 0.8, and that gives you 0.32. Question 6. Find the value of 10 palm 0. The permutation of 10 items taking 0 items at a time. Yeah, this is covered under a fundamental counting principle. So we use the formula n factorial divided by n minus r factorial, and when you do that, you get 1. So please, when you view the prerequisites, then you have a better understanding of what we did, because we have done this, you know, we did it in our previous videos. Question 7. The probability that a person selected at random from the city of Y, this is another city, Y. City of Y, Arizona, earns more than $75,000 per year is 10.5%. The probability that a randomly selected person from the same city earns more than $75,000 per year, given that, so this is a conditional probability, given that the person has earned a bachelor's degree, is 10.5%. The same. Are the events earn more than $75,000 per year and earn a bachelor's degree independent? So we have two events here, okay, and we can call it event A and event B. The first event is that event that a person selected at random earns more than $75,000 per year. And the second event is the event that the person selected at random has acquired a bachelor's degree. So they are asking us whether the two events are independent. The two events, the probabilities of those two events, one is just the actual event, while one is the actual event given the second event. Okay, I want you to understand that. Let's say that event A is the event that the person selected at random earns more than $75,000 per year. So that's event A. Then let's say that event B is that the person selected at random earned a bachelor's degree, event B. So this is probability of event A is 10.5%. And if you read this, the probability that the selected person earns more than $75,000 per year, which is probability of event A, given that the person has earned a bachelor's degree. So this is probability of A given B. So we have probability of A to be 10.5%, and then the probability of A given B to be 10.5%. Are those two events independent? And we say yes, they are independent events because they have the same probability. Probability of A and then probability of A given B. If they are the same, they are independent events. Now, the question you will ask me is, why? Explain. How is it so? Okay. So we have, I have just talked about this. Denote the events A and event B. If we look at the conditional probability formula, probability of A given B is probability of A and B divided by probability of B. B was the one given. So when you solve for this, solve for probability of A and B, you can multiply both sides by the denominator, LCD, which is the probability of B. So when you do that, you have that probability of A and B is the probability of A given B times the probability of B. Call this equation 1. Then we also have from the multiplication law for independent events, we have that the probability of A and B is the probability of A times the probability of B. So these two are the same. Okay, if equation 1, you have probability of A and B. Equation 2, you have the probability of A and B. So what you might want to do is just equate the two, combine the two equations. This equation 1 is equal to equation 2. Okay, and when you do that, because these are the left hand side are the same, so just equate the right hand side. So we have that the probability of A given B times the probability of B is equal to probability of A times the probability of B. Equation 1 is equal to equation 2. So when you do that, you can now divide both sides by the probability of B. And when you do that, you have that probability of A given B is equal to probability of A. And that was what we found out. 10.5% is 0.105. So this happened on one condition, that this is the multiplication law for independent events. So for them to be the same, it will only apply to independent events. If it is not the same, if the probability of A given B is not equal to probability of A, then the events are not independent events. Does that make sense? Please let me know. So whenever we say that two events are independent, okay, we have some things to say. Okay, we have some conditions. Number 1, probability of A given B is also equal to probability of A. Probability of B given A is also equal to probability of B. Then we can also say that the probability of A and B will give us probability of A times probability of B. So you can actually say that the probability of A and B is equal to probability of A given B times probability of B. Also, you can also say that the probability of A and B is equal to probability of A times the probability of B given A. Does that make sense? Okay. Question 8. The probability that a person selected at random from the city of Y, Arizona, earns more than $75,000 per year is 10.5%. The probability that a randomly selected person from the same city earns more than $75,000 per year, given that conditional, okay, condition, given that the person has earned a bachelor's degree, is 21.5%. Are the two events independent? In this case, the probability of A is 0.105. Probability of A given B is 0.215. They are not the same, and if they are not the same, folks, the events are not independent events. Okay? Question 9. A ball is drawn at random from a bag containing 2 yellow balls, 5 green balls, and 8 black balls. Find the probability that the ball is yellow or green. So first of all, we get the sample space, 2 plus 5 plus 8. That gives us 15. The cardinality of event yellow is 2. Cardinality of green, 5. Cardinality of black is 8. So you ask yourself, when you're drawing probability that the ball is yellow or green, when you pick a ball, okay, you draw a ball, it could be yellow or it could be green. There's no way it can be yellow and green. You're just drawing one ball, and that one ball could be yellow or it could be green. So there's no way it could be both yellow and green. So because of that, we say that the events are mutually exclusive events. Okay? And this is a addition law. You use the addition law. And we did that in a previous question. So you just add it up. Yeah. You can either draw a yellow or a green ball. There's no way you can draw a yellow and a green ball. Remember, they said that find the probability that the ball is either yellow or is green. You're just drawing one ball. You're not drawing two balls. Okay? Question 10. A baseball player hit 67 home runs in a season. Of the 67 home runs, 25 went to right field, 22 went to right center field, 9 went to center field, 8 went to left center field, and 3 went to left field. What is the probability that a randomly selected home run was hit to right center field? Just one, not two. A randomly selected home run. So the cardinality of the sample space is 67. Okay, and if you add this up, it should give you 67. If you add up 25, 22, 9, 8, 3, you add it up, it should give you 67. So what is the cardinality of the right center field? That's 22. And this is the probability formula. We discussed this in Introduction to Probability. So B part of the question, was it unusual for this player to hit a home run to right center field? When you do 22 divided by 67, calculator. When you do 22 divided by 67 and it's greater than 0.05, we discussed this in previous videos about probability of events that will be considered usual or unusual. In this case, it's greater than 0.05, so because of that, it's not unusual. Question 11, the events of an experiment. Okay, you have the event A is 6 and 7, B is 10, 11, 12. The sample space is 1 through 12. And you have that the events A and B are subsets of the sample space. So assume that each outcome is equally likely. Okay. We have the cardinality of A is 2 elements in the set. Cardinality of B is 3 elements in the set. And the cardinality of the sample space is 12 elements in the set. So list the outcomes in A or B. A or B. Okay, 1, 2, 3, 4, 5. That's 5. Now, find the probability of A or B by counting the number of outcomes in A or B. So that gives you 5 out of 12. C, find the probability of A or B using the addition law. Addition law. Okay, and with the addition law, we have that this is the probability of A plus probability of B minus probability of A and B. But if you look at A and B, they don't have any they don't have any element in common. So they are mutually exclusive events. A, 6, 7, B, 10, 11, 12. So they are mutually exclusive events. So probability of A and B is 0. That's why I know it's 0, so I didn't put it. Minus 0. And if you do that, it gives you 5 out of 12 minus 0, which is 5 out of 12. Okay. I can probably put it, I can go ahead later on after this video and put it minus 0, which is now 5 out of 12. Question 12. The probability that a randomly selected 3-year-old dove will live to be 4 years old is 0.92399. So we say let the dove be D. A, what is the probability that 2 randomly selected 3-year-old doves will live to be 4 years old? So you just multiply the two probabilities. It gives you 0.85376. You round to 5 decimal places as needed. So that means if you multiply it and it gives you 4 decimal places, you just leave your answer in 4 decimal places. But if you multiply it and it gives you, if it gives you 5 decimal places, you leave your answer in 5 decimal places. If you multiply it and it gives you more than if the answer gives you more than 5 decimal places, then you round to 5 decimal places. We talked about this before in prior videos. As needed, what does it mean? So you can either do squared or you multiply that, okay, because this is exponent squared. 0.85376. That is what you get. B, what is the probability that 5 randomly selected 3-year-old doves will live to be 4 years old? So 0.92399. So some people will come and do times 0.92399 times 0.92399. Come on now. You did exponents. All I need, I press this, x raised to power y, and it is 5. Bam! 0.67349, but this is more than 5, so I call it 1, add it to 49, it becomes 50. 0.67350. Okay? To save your time. Question 13. For a parallel structure. Okay, I'm gonna fix it. Question 13. Typo, I'm sorry. For a parallel structure of identical components, the system can succeed if at least one. So there's something I wanna if at least one of the components succeeds. See that? If at least one of the components succeed, then the system will succeed. So at least one could succeed, or both of them could succeed. Okay, if you have two identical components, if one succeeds, the system will succeed. If the both of them succeeds, the system will still succeed. So at least one means 1 and above. Okay, assume that components fail independently of each other and that each component has 0.17 probability of failure. So if it has 0.17 probability of failure, that means the probability of success will be 1 minus 0.17. Okay, just know that. Now let's say S is success and F is failure. A, would it be unusual to observe one component fail? We say no, because the probability of the failure is 0.17. Probability of failure of each component is 0.17. It is greater than 0.05, so it will not be unusual to observe one component fail. B, would it be unusual to observe two components fail? So let's find that for two components to fail, it will be 0.17 squared. You can do 0.17 times 0.17, or you just do squared. Okay, or you do 0.17 and you raise this to 2. But the easiest thing is to do squared. So this is 0.0289. It is less than 0.05. So it will be unusual. C, what is the probability that a parallel structure with two identical components will succeed? So remember, for the identical components to succeed, all we need is for at least one of the components to succeed. So we can have this, we have the first succeeds and the second fails, or the second succeeds and the first fails, or both of them succeeds. These three conditions can apply for the components to succeed. You understand what I'm saying? Because the question here says if at least one of the components succeeds. So if we have a structure with two components, then what we need is, okay, we have the first component and the second component. Well, they told us that for the system to succeed, it needs at least one of the components to succeed. So that means that the first component might succeed and the second might fail, or the first component fails and the second component succeeds. The system will still succeed, or both components succeed. Okay, so you have to take note of that. If you do that, the probability that the first succeeds, second fails, is 0.83 times 0.17. Remember, we said that probability of success will be 1 minus 0.17. And that gives you 0.83. So this first condition, first succeeds, second fails, is 0.83 times 0.17. Or it could be that first fails, second succeeds, 0.17 times 0.83. Or both of them succeeds, which is 0.83 times 0.83. You add all of them, it gives you 0.9711. Does that make sense? Okay. Remember, our F is the failure and X is success. Yeah. Question 14. Among 40 to 46-year-olds, 35% say they have driven a car under the influence of alcohol. Please don't do so. Which means 35%, which means the probability is what? 0.35. Okay? That tells us right away that the probability of selecting a person among 40 to 46-year-olds who have driven a car under the influence of alcohol is 0.35. Suppose two 40 to 46-year-olds are selected at random. This case is two of them. Okay, and we say let driven under the influence of alcohol, let it be A. What is the probability that at least one has not driven a car while under the influence of alcohol? Round to 4 decimal places as needed. So at least one means greater than or equal to 1. So if at least one has not driven, among two people you select, what is the probability that at least one has not driven? So it could be that the first one has not driven and the second one has driven. Or it could be that the first one has driven and the second one has not driven. Or it could be that both of them has not driven. So, but probability that they have driven is 35%, which is 0.35. So the probability that they have not driven is 1 minus 0.35, which is 65%, which is 0.6. I'm sorry, 1 minus 0.35, which is 0.65, which is 65%. Okay, so you have to consider the three cases. Case 1, first one has not driven, second one has driven. Or first one has driven, second one has not driven. Or both the first and second has not driven. Okay, when you do that, and you add it up, you get 0.8775. B, what is the probability that at least one drove a car while under the influence of alcohol? So it's still the same reasoning. Okay, first one, at least one means greater than or equal to 1. First one has driven, second one has not driven. Or first one has not driven, second one has driven. Or both of them has driven. Okay, so when you do that, you get 0.5775. Question 15. Two cards are randomly selected from a standard 52 card deck. So when we talk about the 52 card deck, we have that the number of kings, we have K, let's say K to be king. The cardinality of the sample space is 52. And in a 52 card deck, we have that the number of kings is 4. A, what is the probability that the first card is a king and the second card is a king if the sampling is done without replacement? So this is a condition of without replacement. Okay, so let's say you have the card, 52 card, in a, you have it in a container. You close your eyes, you pick a card. Let's say you picked a king. The probability of picking a king was that first time is 4 over 52 because you have 4 kings in the 52 cards deck. Okay, and you picked a king and you were mad and you say, no, I don't want king, and you threw it out. You didn't replace it. Okay, when you don't replace it, those are dependent events because whatever you're picking the next, and we explained this in the introduction to probability. Whatever you pick next, the probability has already been affected because you did not replace the first card you picked. So the probability of the second event will be affected by the probability of the first event because a card is now missing. Why? Because the sample space has been affected. Okay, before you pick the first card, the sample space was 52. When you picked the first card, it was the king. You threw it away. You did not replace it. So the sample, before you now make a second pick, the sample space is now 51. That is those two events, the first event of picking a king and putting it in the trash, and the second event of picking any other card. Those two events are dependent events. Okay, because the second event was dependent on the first event. Okay, in this case, let's say both the first and the second pick will be a king. Okay, so in this case, you don't just affect the denominator, you also affect the numerator. You picked up the first card, it was a king. You put it in the trash can. So before you make your second pick, okay, the 52 cards will now be 51 cards. And it was 4 kings before, but before your second pick, it will now be 3 kings. So the probability of the first event, okay, which you just started, will be 4 over 52. You trashed it, the 52 becomes 51, and the 4 becomes 3. So the probability of making it that the second event will be a king will be 3 over 51. See that? And that's how we got approximately 0.005. Okay, what if it was done with replacement? That's fine. This is with replacement condition. So these are independent events. You just multiply the two probabilities. They are independent events. This case is dependent events. Without replacement is dependent events. With replacement are independent events. Question 16. The table shows the math guys and the art guys. Which one do you go for? Do you go for math or do you go for art? Well, go for math. Math guys and art guys among high school students, 10th, 11th, and 12th grade students in a certain school. And you have to round all your answers to 3 decimal places as needed. So we have 232 10th grade math guys. We have 53 12th grade art guys. We have 510 11th grade students that are both math guys and art guys. We have 733 math guys from 10th grade, 11th grade, and 12th grade. We have 1,157 art guys from 10th grade, 11th grade, and 12th grade. I mean, it's good if you kind of, you add up all this, it gives you this. You add up all this, it gives you this. You add up this, we have 1,268 10th grade students. We have 510 11th grade students, which include both the math guys and the art guys. And we have 112 12th grade students. All together, all the students we have in this for both 10, 11, and 12 grades that are both math guys and art guys are 1,890 students. Okay, so it is good you arrange your table like this and be able to interpret it well, just like we did before you answered your question. You add up all the math guys, gives you 733. You add up all the art guys, gives you 1,157. You add up all the 10th grade students, gives you 1,268. Add up the 11th grade students, gives you 510. Add up the 12th grade students, gives you 112. Okay? If you add up all this like this, it gives you 1890. You add up all this like this, 733 plus 1157, it gives you 1890. So, A, if a student is selected at random, what is the probability that the student is a math guy? So we are looking at how many math guys do we have? 733, because they said math guy. Okay, how many students do we have? 1,890 students. So probability of math guy will be 733 divided by 1890, and that gives you approximately 0.388. B, if a student is selected at random, what is the probability that the student is 11th grade is in 11th grade. So in this case, we're only dealing with 11th grade. And that will be 510 over 1890. Okay? That gives you approximately 0.270. C, if a student is selected at random, find the probability that the student is in 11th grade or 12th grade. So we are looking at 11th grade is 510, 12th grade is 112. So if you add both of them, 510 plus 112, it gives you what? 622. Now, these are mutually exclusive events because you cannot have a student that is in both 11th grade and 12th grade. So these are mutually exclusive events. Okay, so you add it up and divide by 1890. That gives you approximately 0.329. D, if a student is selected at random, find the probability that the student is in 11th grade and is a mad guy. So how many 11th grade mad guys do we have? 442. Okay, so you have 442 divided by 1890. And that is approximately 0.234. E, if a student is selected at random, find the probability that the student is in 11th grade or is a mad guy. So this is also, anytime you see or, you talk about addition law. Okay, some textbooks call it addition rule. So we find, okay, probability that 11th grade or mad guy. So it could be probability that is 11th grade plus probability that is a mad guy minus probability that is 11th grade and mad guy. Okay, just like we did here, 11th grade or 12th grade or 12th grade. In this case, it's still addition law, but the only thing is that the probability of 11th grade and 12th grade is 0 because these are mutually exclusive events. They are mutually exclusive events. You can't have somebody that is in 11th grade and 12th grade. Now, but can you have someone that is in 11th grade and is a mad guy? Yes, you can. Okay? So when you do that, 11th grade plus mad guy minus 11th grade mad guy. You do that, this is 510 for the 11th grade. You have 510. Okay. Mad guys, you have 733. Then 11th grade mad guy minus 442. Please, addition law, take note of that. Yeah. And that gives you approximately 0.424. You just do the fractions. F, if an 11th grade student is selected at random, what is the probability that the student is a mad guy? So this case, you're looking at mad guy from 11th grade. So please take note of that. Mad guy from 11th grade. In this case, we are not looking at the entire student population. We are not. We are just looking at a sample of the students, and the sample is from 11th grade. So in this case, the cardinality of the sample space will be only 11th grade students. And what would be our event? Just getting a mad guy from the 11th grade student. So take note of that, please, in this case. It did not tell you if a student is selected at random, no. It told you if an 11th grade student is selected at random. So in this case, our sample space will just be 11th grade students. Okay, please take note of that. In the previous questions they were asking, they say if a student is selected at random. If a student is selected at random, you see that. If a student is selected at random. Because this is selecting a student at random from the school. It could be a math guy, it could be art guy, it could be 11th grade, it could be 10th grade, it could be 12th grade. But in this case, they said if an 11th grade student is selected at random, so our sample space will now change to 11th grade students only. Okay? G, if a 12th grade student, the same thing here. If a 12th grade student is selected at random, what is the probability that the student is a math guy? So here, our sample space is dealing with 12th grade. And then what will be the cardinality of the event space? We are looking for an event of selecting a math guy from the 12th grade students. So this will be cardinality 12th grade math guys divided by the cardinality of 12th grade students. Okay? And when we do that, we have approximately 0.527. H, if a 10th grade student, the same thing here, the cardinality of the sample space here would be 10 grade students. Okay? If a 10th grade student is selected at random, what is the probability that the student is a math guy? The same thing. Okay? This will give you approximately 0.183. I, if two, not I, but you, don't mind me. I, if two 11th grade students, okay, two 11th grade students. So the same thing here, our cardinality of the sample space will be 11th grade students. But in this case, we're looking at 2. If two 11th grade students are selected at random, find the probability that both are math guys. Okay? So these are independent events. We just multiply it. 442 over 510. Because probability of selecting a math guy from 11th grade is 442. Okay? Over 510. So we just multiply those. And it gives us approximately 0.751. Okay. So thank you so much, students, for listening to this video session. If you have any questions, please feel free to ask me. And you have a great day.